Okay. So today we're doing what we call the reaction quotient, and it falls under the syllabus outcome. Perform calculations to find the value of KEQ and concentrations of substances within an equilibrium system, and use these values to make predictions on the direction in which a reaction may proceed. So, um, here's the answers for the revision questions. Our equilibrium constant, it's a numerical value that shows us where the equilibrium lies in a chemical system. It's calculated by substituting in concentrations of all the reagents at equilibrium. If the value is less than 1, the equilibrium favors the reactants. If the value is greater than 1, the equilibrium favors the products. Now, what we're doing today is what we call the reaction quotient. Basically, using the K equation when an equilibrium system is at equilibrium gives us the equilibrium constant. However, if the system's not yet at equilibrium, using the K equation gives us what we call the reaction quotient. Now it basically shows us where the ratio of products to reactants is and which way it should go to get to that equilibrium constant. So remember, our KEQ will always give us the value of the equilibrium constant when it's at equilibrium. If it's not at equilibrium, then it'll give us a different number. But from that information, we can determine which way the reaction has to go to come back to equilibrium. Okay, and it is tied in with that Le Chatelier's principle. So the reaction quotient Q gives us information on how the equilibrium will move based on the current concentrations of components. If Q is smaller than KEQ, then there are currently too many reactants in the reaction vessel, and so the equilibrium will shift towards the products. Now, if we have a think about KEQ, okay, we know it's products over reactants. Okay, um, yeah, like that. If our Q ends up being smaller than KEQ, it means that the number at the bottom is either bigger than it should be, or the number at the top is smaller than it should be. So it's one of those two things, or it could be a combination of both. Basically, if there's too much at the bottom, it needs to move towards the top. So it needs to go from reactants to products. Okay, and again, that comes back to that whole fraction thing, where for example, 2 over um, if it needs to be 2 over 7, but it's 2 over 9, okay, this being less than this, some of that needs to go up to there to equalize it. Okay, so that's just a kind of a crappy example. You can ignore that if you want, but the basis is that if Q is less than KEQ, then the reaction goes to products. If Q is larger than KEQ, then there's currently too many products in the reaction vessel. And so the equilibrium will then shift towards the reactants. So again, thinking about our products over reactants, if there's too many products, so if K is bigger than KEQ, then there's too many products, so some will go towards the reactants to even it out to get to that KEQ value. Okay, basically, if KQ is greater than KEQ, then it goes towards reactants. So I was kind of explaining this before, but KEQ is a fraction, and so we can use that to see what will happen. So if Q is bigger than KEQ, then either the numerator is too big or the denominator is too small. So if the numerator is too big, then there's too many products, so the equilibrium will shift towards the reactants. Or if there's not enough reactants, then there will be the equilibrium will shift towards the reactants. Okay. So if we've added products or if we've taken away reactants, it goes towards reactants. If Q is smaller than KQ, either the numerator is too small or the denominator is too big. So either way, we're going to get that shift towards products. Okay, so basically either we've added some reactants or we've taken away some products, and so it's going to move to try and equalize the change. So that's our mini summary. If Q is greater than KEQ, reaction will move towards the reactants. If Q is less than KEQ, the reaction will move towards the products. So how do we put this into, as an example? So have a look at our Haber process equation yet again. Nitrogen plus 3 hydrogens is in equilibrium with 2 ammonia. So imagine that at a certain temperature, this equation has a KEQ of 10. Determine the direction of the reaction if the concentration of the reagents are as listed below. So hydrogen is 0.2 molar, nitrogen is 0.8 molar, ammonia is 0.5 molar. So this is basically, there's 3 main steps to answering these kinds of questions. Sorry. Firstly, we need to find the K equation. Secondly, we need to find out our reaction quotient, so our value for Q. We then need to compare it to our KEQ value. Now, sometimes these questions might trick you and give you a number that's equal to KEQ, in which case you say it's at equilibrium. Okay, so if Q equals KEQ, we're at equilibrium. So first step, products over reactants equals K gives us, so for this equation, we should get that. Okay, so ammonia squared over nitrogen times hydrogen cubed. We then substitute in the values that we have. Now these are not at equilibrium, so we no longer write it as KQ equals whatever, we write it as Q. And so Q is going to be the same equation. We're going to substitute in the values, and we're going to get 39.06. So our KEQ is 10. Is that equal? No. 39.06 is not equal to 10. So what is it? Well, Q is greater than KEQ, and so the reaction will move towards the reactants. So basically, at this time point where we took those concentrations, it's not at equilibrium. It's going to shift towards the reactants to come to equilibrium. Okay, so there's too many products in this one. Now, next example. Good old nitrogen plus oxygen gives us 2NO. It has a KEQ of 170. Determine the direction of the reaction if the concentration of the reagents are 0.5, 0.2, and 4. So again, first thing we do, for our equation, we write the K equation or our K expression. So it's KEQ is NO squared over N2 times O2. Again, we substitute the values into the K equation, changing it to Q because it's not at equilibrium. So we have Q equals NO squared over N2 times O2. Put our values in, use our calculator, get an answer, 160. We then compare that to our KEQ. So we got a value of 160, KEQ is 170, so they're pretty close. But Q is less than KEQ, so the reaction will move towards the products. Okay, so there's not enough products in that reaction. For equation 3, let's say we have this equation again, 2SO2 plus O2 is in equilibrium with 2SO3. Now imagine that has a KEQ of 6 times 10 to the negative 2, so 0.06. Determine the direction of the reaction if the concentrations of the reagents are 0.5, 0.2, 0.1. Same thing, what we do, write the K equation. So for this equation gives us this KEQ equation. So SO3 squared over SO2 squared times O2. We then substitute the values into the K equation, again labeling it as Q because it's not at equilibrium. So Q is that, put our values in, we get an answer of 0.2. Okay. So we get a value of 0.2 for Q, but KEQ is 0.06. And so Q is bigger than KEQ, so the reaction will move towards the reactants. So in summary, the reaction quotient Q measures relative amounts of products and reactants present at any point in time in a reaction. If Q is equal to KEQ, then the reaction is at equilibrium. If Q is bigger than KEQ, then the reaction will move towards the reactants. If Q is less than KEQ, then the reaction will move towards the products. And that is all for today. Thank you.